Alright guys, we're going to get the notes done. This is the last stuff we're going to learn for the whole quarter. So after this, it's just getting ready for the test and getting ready for the final. This is the last bit of information you need to know. Well, no, we're fine now. We just didn't get a chance to do the project. So we may do the project next term or the term after. Okay. So the last section is about inverses. Okay. Okay, we'll go that way. Let's just start with a basic idea of an inverse. So you guys are used to seeing these by now. Let's say in set A, we have little a, little b, little c. And let's say here we have little d, little e, little f. And our function f takes a to d, b to f, and c to e. So here's how I want you guys to think about this. We don't really know what rule f is or what it does. You might be taking the input, which is a, multiplying it, adding it, doing all these different things, but eventually the answer is going to be d. Does that make sense? Okay? In other words, f of a would equal what? D. F of b in this case equals E. Oh no, I messed it up. You're right. F. And then F of C is E. Okay, so that's what F does. It takes A, B, and C and gives you outputs of D, E, F. But sort of switched here as I messed that up. Now, the inverse does the exact opposite. So it's basically going to undo whatever F did. So for instance, if the function rule is to multiply, add, and subtract some stuff to get D, then the inverse is going to unravel and undo all of that. And here's the notation we use. And now it's going to take D back to A, E back to C, and F back to B. So that's what the inverse does. Okay? So a couple things I want you guys to see now. If I asked you to find the inverse value of D, what do you get? Goes back to A, right? What is the inverse evaluated at E?
C.
E goes back to C, and then the inverse evaluated at F is B. Does everybody kind of understand that concept? Okay? So now a few things I want you to notice. If I did the original function, composed it with the inverse, let's say of A, let's do that with, oh, sorry, hold on. I messed that up. Let's say I have the inverse composed with f of A. What do we get? Well, what's f of A? F of A is D. And now do we know what the inverse evaluated at D is? A. In other words, when you do the composition of the inverse with F, everything pretty much canceled out and your answer was A. Do you guys see that? Okay, let's see if that works the other ways too. What if I did, let's do F of F inverse of, let's say, D. Bless you. Do we know what F inverse of D is? Do we know what F of A is?
D.
D. Here again, we get the same idea. Okay, so that's kind of the idea of an inverse. It takes the original function and undoes whatever that did, gets you the original input. Does that make sense? And vice versa. Okay, so here's the formal definition. We say F and G, we're calling it F inverse, but F and G are inverses of each other. If and only if, that's the abbreviation for if and only if, F of G of X. So if these are inverses, what should my answer be here? Look at what happened up here.
X.
Answer should be X, right? Whatever X is. And if they're inverses, it should also work the other way. This is provided that X is in the domain. X is in domain of G and then F. And I think you guys, well, maybe you didn't notice, but why didn't this work up here? Why did I scratch this out? So, do you guys see the mistake I made? Right over here, I was writing F inverse of A, and I said, whoa, hold on, I don't want that. Well, let's see why.
Because the inverse is if you want, like, A is going to be your given sign. It's not going to be
Yeah. You see how A is not part of the inverse here? So this, even though all these canceled out, right? You got A here, you got D there. This would not work because there's no A value in here. Does that make sense? So this is what this means, is that this X value has to be part of G, and this X value has to be part of F in order for this to work. Okay?
Wait, would you write?
Provided that X is in the domain of F and G, or G and F. Basically, whatever's on the inside here. So maybe we can rewrite this. In order for this trick to work, X must be in the domain of inner, does that make sense if I say inner function?
Yeah.
So if this is going to work out, then X has to be defined for G. And if this is going to work out, then X has to be defined for F. Okay, and what we mean by the nice little shortcut or the nice trick is these just cancel out and you get X. That's what inverses do. Okay? So that's one way to look at them. So I'm going to try to represent all these inverse ideas in lots of different ways because there's different ways to look at it and you should be comfortable with any format. Here's another idea. Okay, so we're not even doing inverses yet. We're just looking at the ideas behind inverses. Let's say I have a table, X and Y, and this is the rule for F. And in the table we have 1, 3, 5. And when I plug those in for Y, I get 7, 9, 11. What's the table for the inverse going to look like? If this is the table for the original function. Exactly. Everything just flips. 7, 1, 9, 3, 11, 5. So another idea is that the X's and Y's switch for inverses. Which is actually really cool because if you know what a graph looks like, you don't even have to find like a rule for the inverse. You can just switch all the X's and Y's and you already know what the inverse graph looks like. Bless you. Okay. Any questions so far? We haven't actually found inverses yet. We're just kind of looking at some big ideas here. All right. So there's a few things you need to be able to do. Find inverse functions. That's one. There's a couple ways to do that. You need to also know when those inverse functions actually exist. So let's actually start doing this stuff. So define an inverse. The most traditional method is to switch x and y, because that's what happens. We saw that up here and with the bubbles, how everything just flips around. Then you solve for y. And whatever your answer is, this is your inverse. Somebody just very slowly open a soda bottle.
No, but I heard that.
There's a device making that hissing noise?
It was on the wall.
Oh. Well, that's freaky.
What happened?
Don't worry about it. We're all safe. It's okay.
Are you sure?
Yes,
I'm sure.
Okay.
Okay. The second option. This is actually a really cool option. Okay. You write out what the function does to x and then you work backwards, and I'll show you what this means, obviously, and undo it. This is the inverse after you do that. Okay, so we'll do a very basic example here. I should clarify that this option here works as long as you only see one x. So if you have like an x squared, an x to the 4, and a bunch of x's everywhere, you're not going to do this option. But if it's just like a single x with a bunch of other stuff going on, this option will always work.
It's more than
Wait,
If it could be more than linear. I just mean like if you have an x cubed, that's fine. It just can't have an x cubed and then another x somewhere else. Yes.
so we wouldn't be able to do, like, you know how some problems, there's like the x squared plus something, x plus something.
Right.
You could end up solving and finding two x's. You can't do that.
You can't do that with this, no. In fact, you're going to see why in just a minute here, okay? So here's an example. We'll work it both ways, okay? Let's say f of x equals x cubed minus 1. And we want to do a few things. We want to, 1, find the inverse. 2, graph both f and f inverse. Let's see, what else can we do with this? And 3, show algebraically. So you know, we'll just do this one example and do everything we need to do with it so that everything's clear. Show algebraically that f and f inverse are actually inverses. Okay, so we'll do all three of them very carefully. So part 1, finding the inverse. I'm going to do this with the first option. Okay? F of x is really the same thing as what variable? So I'm going to write it as y equals x cubed minus 1. My initial thing that I have to do here is to literally switch x and y. So if I see y, I write x. If I see an x, I write y. So that's the first step. Does this look familiar, you guys?
Kind of.
Okay, you've done this before, so hopefully I'm not going too fast. Second, now I just solve for y.
Oh,
So how can I get y alone?
Plus 1.
Add 1, And then how do I undo a cube? Cube root it? So now y equals the cube root of x plus 1. This is the inverse. So I would always write it over. F inverse of x equals cube root of x plus 1. What's that? Oh, sorry. Erica?
Will we ever be using this to like find like a range or something, or is this just?
It's actually very similar to finding the range, except we switched the x and y first. Okay? When we did the domain and range earlier, we didn't find the inverse necessarily, but that's the other thing that should happen. Maybe we can. You know what? Let me touch on that later. Let's finish this. But you hit something right on the head that we need to talk about, which is really cool. Let me show you the other option, which I think some of you are going to like. Okay? So, here's our original function. There's our inverse, yay. We'll graph them later. Here's the other option to finding an inverse. Okay, so if we look at the original function, here's what I like to do. I just write f, and then underneath it, I'm going to write out what steps are being done. So, for instance, if I follow order of operations, the very first thing I do to x is what? What am I doing to x following? If I were to plug in a number into x, what do I do to figure it out? First, you cube it. So I'm going to do to the third power. After you cube that number, what's the last thing you do? You subtract 1. Okay? So the inverse is going to undo all of that. We work backwards and undo everything. So if the last thing I do is subtract 1, the first thing my inverse should do is add 1. And if the very first thing my original function does is cube, then to undo that, the very last thing my inverse should do is to cube root it. So now how does that translate? Well, now I look at these rules, and I just follow the steps. I say f inverse equals, and I start with x. I always start with x, and then I just do what the rules say. So what does this rule say? It says to add 1, and now it says to cube root all of it. So we still get the same thing. Yes?
Would it say if we have to cube root something specifically?
Yes. Yes, it would. Okay. Any questions on that? All right, let's look at the second part of it, which is to graph both of them. Okay, so here's the cool thing I was trying to show you guys earlier. I don't really know what this looks like. We haven't really done cube roots, have we? But have we done this graph? We know what that looks like, right? So part 2. Let's graph.
Isn't it going to be just on its side?
In the end, yeah. Let's graph f. The cubic function. Did you guys memorize those points yet? Because you got a quiz tomorrow, right? 0, 0, 1, 1, 2, 8.
Negative 2, negative.
So what is a minus 1 going to do?
It's just going to move it down 1.
Everything just goes down a unit, right? So instead of 0, 0, I'm down at 0, negative 1. And then at 1, 0. And then instead of 2, 8, I'm at 2, 7. Does that make sense? Bless you. So, sorry. Is that better? So, and then if I go the other way, usually it's negative 1, negative 1, right? But everything's down a unit. So I'm going to go negative 1, negative 2, and then negative 2, not negative 8, but negative 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I know it's kind of hard without graph paper. You guys will have graphs given to you when you do this. But so this is the original function f. No surprise there, right? So here's f. Okay? Now, maybe after we do this, you'll kind of know what a cube root graph looks like. But the best way to graph an inverse, if you already have a perfect graph for the original, is to what?
Plug in the same ones.
What about the points?
Plug in the same ones.
Well, we don't need to plug in anything. What happens with the x's and y's for inverse functions? They all switch, right? So can't I just look at this and say, all right, so here I'm at 2, this was 2, 7, right? If this is at 2, 7, then what point is going to be on the inverse?
7, 2.
7, 2. So I'm going to go out to 7, 2, and there's 1 point. This point here that was at 1, 0 becomes 0, 1. You guys with me?
What?
This point here that's at 0, negative 1 becomes negative 1, 0. This point that was at negative 1, negative 2 becomes negative 2, negative 1. And then this last point, what was it? It was negative 2, negative 9, right? So just flip everything. Now it's all the way back here at negative 9 and then negative 2. And now you can kind of see the shape there, can't you? So this green graph right here is the inverse graph. And you know what? I didn't even have to make a table for it or do anything. If I know what the original looks like, I know what the inverse looks like. Okay? Do you guys notice anything else?
It's like the same.
It's
Same shape.
like you took it and you.
Yeah, I mean, it kind of rotates a little bit. If you guys were to draw a line that was like a mirror or like a reflection line, what would it look like?
Oh, it's across the. Is that what the origin?
So through here, where? Where do I draw the line?
The
Straight up?
like diagonal.
Like this?
Yes.
Do you guys see the reflection there?
Yes.
What line is this?
Origin.
Well, it goes through the origin. What's the equation of this line? It's y equals x. It's not a coincidence. Because what happened when we did all the, if you did inverse, evaluated with the original, it always unraveled and gave you just the x, right? So all these things are intertwined and they're all connected.
That's the same thing as square root. Like square root and square root.
Yes, exactly. Well, x squared does not have an inverse function. It has an inverse relation, and it would be the same. We'll talk about that a little more later. Okay, are there any questions on how we're getting this? Okay, so a very good thing to write here is that the graphs f and f inverse have symmetry with y equals x line. It's like a mirror. So if you want to know if you graph things correctly, you should be able to do this every time where you take that diagonal y equals x line and it should look like it's a mirror. Do you guys see what I'm talking about? Okay. It did get really hot all of a sudden, didn't it?
Yeah. Maybe it's supposed to be like.
They did not just turn on the heat, did they? It's hot? You guys want to open a window?
Yeah, they did. No! It's actually warm. It's always freezing.
I'm dying up
They
here.
always do this.
I can't even.
Oh my god.
She turned it off. I'm gonna die.
Open the window, Phil.
Okay, did we do all three things yet? Oh, okay. Okay. Last. Right here. So the third thing we have to do, guys. All right, bring it back.
There's a third. Bring it back. Way. Bring it back.
You okay there? So we wanted to do three things. Find an inverse. We did that a couple of ways. Hopefully you guys can do it one way or the other. 2, we graphed both the original and the inverse. No problem. The last thing here. This is kind of tricky, but I'm going to show you the best that I can so that you guys don't mess this up. Because it's not hard. It's just hard to remember sometimes. Whenever it says to show algebraically that these are inverses. So for number 3, we use the fact that f inverse of x should equal x, and f inverse of f of x should equal x. Because if they're inverses, right, they should undo each other and you should just get the input. Okay, so whenever it says to show algebraically that they're inverses, what you want to do, you start with this one. So let's write out what we get. F of f inverse of x means f of, and now I'm just going to write my rule. What's the rule for the inverse? What did we find out? It was the...
I'm confused already. What's that first thing about
I just rewrote this.
Oh.
And now I'm plugging in the inverse. What was the inverse rule that we figured out? It was cube root of x plus 1. So that's going to go here. And now, what does this mean, f of cube root of x plus 1? That means take this, plug it all the way back into the original function. Where is it? Right here. So instead of x, what am I cubing now? I'm cubing the cube root of x plus 1 cubed, and then according to this rule, I am subtracting 1. You guys see what I'm doing there? Because the original rule was x cubed minus 1. Now I'm just plugging the inverse into x. And now what should happen is that everything should cancel out, and you should get x, if this is done correctly. Well, what happens when you cube a cube root? You get whatever's in there, so x plus 1 minus 1, which is x. Okay? So that's half of it.
What?
That shows that it's probably going to be an inverse, but you always have to check the other direction, too. Meaning not f of f inverse, but f inverse of f. So now we should be able to plug in the original function into the inverse, and it should also do exactly the same thing. So let's see. F inverse, what was the original rule? X cubed plus,
Plus or minus?
wasn't plus, was it? It was minus? Thanks, guys. And now I'm taking x cubed minus 1. I'm plugging it into my inverse rule, so I'm going to do cube root of, instead of x cubed minus 1 plus 1. Let's just make sure that works out. If you combine some like terms, the negative 1 and the positive 1 cancel. You get cube root of x cubed, which is x. So both ways it works out. This proves algebraically that these are actually inverse functions.
Wait.
Yes, Erica?
How come when you're proving like the inverse, the minus 1 is outside of the cubed, and then for like what you just did?
Okay, here. Let me. I have an idea. The original function was x cubed minus 1, right? And then we found the inverse was cube root of x plus 1. So basically, here's what's going on. You got it?
Yeah, I got it.
So when you do this, first you take the original function, you take all of it, plug it into x, and make sure that it all cancels out and you get x when you're done. And then the second thing you do now is take the inverse and plug it in here. Does that make sense? And then it'll all work out and cancel out and give you x. Okay, so those are the three things you need to be able to do. As far as... Okay, so this is the last thing then, I think. We did the graphs, we did that. We should be in good shape. One-to-one functions. So, one-to-one means every x, so every x has a unique, do you guys know what unique means? Unique means, like, if, for example, if 2 has an output of 5, then 3 has to have a different output. That's what unique means, like different. You can't have any repeated y values, okay? So, for example, if I looked at a table, 1, 2, 3, and I saw 5, 5, 7, this would be a function. However, it's not one-to-one because 1 goes to 5 and 2 also goes to 5. Does that make sense? But not one-to-one.
So now it's like a more specific function.
Well, no, it just, what it means more specifically is that anything that's one-to-one will not have an inverse function.
to be like A, B, C, and D, F. A equals to E, B equals to F, and then C equals to D. It cannot be like A to B, and then A to D, and then B to D.
Right. Exactly. They have to go to different y values. Okay? Here's a visual way of determining if functions are one-to-one. We'll do two examples here. Think about what the definition was, that every x has to have a different y, right? So if I'm looking here at x equals 1, 2, and so on, right? And I go over here and look at the negatives. Will every x have a different y value?
Yes.
Okay. What about over here? Why not? Give me one example where the y values are the same.
Y.
If I go to 1, and if I go to -1, you guys see how we have the same y values? What kind of line did I just draw? This is a horizontal line. Okay. If we combine vertical line test and create a new one that we call horizontal line test, that's a quick way to see if something's one-to-one. So for example, if I'm looking at this graph up here, does it pass vertical line test?
Yes.
This passes vertical line test, right? And does it also pass a horizontal line test, where it only crosses each place once? That's how we know that this is quickly one-to-one. This one, however, even though it passes vertical line test, which means it's a function, it does not pass the horizontal line test. So that means that this is not one-to-one. And so all that means is that there is no inverse function. You can still find an inverse relationship, but I think you guys saw with the example we did here. Let me just put it up real quick. Essentially, when we had our original graph, do you guys kind of see how it kind of flipped around and went this way for the inverse? If you imagine doing that same thing with the parabola, now it's going to be what? Kind of sideways like that. You see how it won't pass the vertical line test if you flipped it on its side? Okay? That's what the horizontal line test is telling you. Okay? Does that kind of make sense? Okay. That's it.